Welcome to this application presentation of DIC, or digital image correlation, being used for axial and biaxial tensile testing. Application 1 was a steel bar tension test measured using the multicam DIC system. The test object was a steel bar of a rectangular cross-section, the width was 10 mm with a thickness of 5.5 mm. The measurement objective was to measure the thickness of the steel bar via a double-sided or biplanar setup. The second measurement objective was to determine and measure the Young's modulus and compare the Young's modulus with the input Young's modulus. Measurement objective 3 was to compare the UTS between the engineering and true stress assumptions. Objective 4 was to measure the plastic strain ratio, or the R value. To the right, we see the individual fields of view for cameras 1 and 2 from the front side and cameras 3 and 4 from the rear side. Presented in each of the fields of view is the ISTA40 2D overlay visualization of the Lagrangian principal strain 1, or major strain in millistrain. The advantage of biplanar or double-sided DIC measurements is that they can provide detailed information on specimen bending and misalignment during a test, which would otherwise not be accessible using a planar or single-sided setup. The different strain distributions on either surface indicates bending or misalignment of the steel bar in the materials testing machine with respect to the loading axis. It can be seen in the video the increasing Lagrangian principal strain concentrates at the center of the specimen right up until fracture. In video 1 shown to the right, we see the ISTA40 3D visualization model of the Lagrangian principal strain 1 in millistrain with one biplanar virtual point gauge. The table plot below shows the thickness difference between the two biplanar points in millimeters with respect to acquisition step. During the end of the tensile test, the coupon specimen undergoes necking, which can be observed as a drop in specimen thickness. The double-sided measurement allows the true stress to be determined through actual measurement of the specimen thickness, rather than using the engineering stress on the basis of the constant volume approximation of the Poisson ratio. In the QR code linked on the bottom left, users can scan and download the double-sided testing application note. In figure 1 to the top, we see the ISTA40 3D visualization model of the displacement with reference step shown in green and the failure step shown at maximum load in red. In video 1 to the right, we see an ISTA40 3D visualization model of the displacement with rigid body motion removed, with the reference step shown in green and the acquisition step shown in red. The table plot below shows the load in kilonewton recorded as an analog input with respect to the acquisition step. It is clear that during the measurement the sample is misaligned in the materials testing machine with respect to the loading axis and as such bends. In figure 1 to the right, we see the materials testing package with the advanced graphical user interface that allows users to plot a diagram of stress versus strain, also the Young's modulus, and saves the data series using one line gauge. The graphical user interface calculates the Young's modulus and finds the yield stress and strain, the 0.2% offset yield stress and strain, the ultimate tensile stress, and also the uniform proportional elongation. Users have the option of defining the cross-section geometries, being a circular or rectangular geometry, and the input dimensions, as well as selecting the stress calculation method based on either the engineering stress or true stress. The measured Young's modulus is 180.57 gigapascals, and the reference Young's modulus for steel is 180 gigapascals. The engineering stress was 595 megapascals, but the true stress was 680 megapascals. In the graphical user interface, users can define the dimensions of the cross-section, the stress calculation method, the strain range to be plotted, the determination of the yielding points, and also the range for the determination of the E-modules. In Figure 1, we can see the ISTRA 4D 2D overlay visualization of the Lagrangian principal strain 1 with one virtual line gauge called line 1. The gauge element is used to calculate the plastic strain ratio, using the ratio of true strain in the width to the true strain in thickness when a specimen is pulled in uniaxial tension beyond its elastic limit. This approach assumes the volume is constant during the test and uses the true principal strains for calculation. In graph 1 to the top, we can see the 2D plot of 248 R-value data points with respect to the true principal strain 1. The average R-value is approximately 0.8.